Welcome to Benchmark. Today we're going to ask the question, how loud is the distortion from my power amplifier? And one of the things I'd like to say is that of all the electronic components in a typical audio system, the one component that's responsible for more distortion in most cases is the power amplifier. But just how much distortion and how loud is that at my listening position? Is this something I should be concerned about, or is it too low in level to be worried about? So let's take a look at 7 top-rated amplifiers that are top-rated by Stereophile magazine. These are the amplifiers that they put on their recommended list, and we're going to take a look at Stereophile's measurement of these amplifiers to answer the question, how loud is the distortion from these amplifiers? So I have a chart here that shows the loudness of various things, from the smallest sound that we can hear, 1 dB sound pressure level, all the way up to 140 decibels, threshold of pain, or above the threshold of pain. And in the middle of this graph, because this graph was created by an appliance manufacturer, they're saying that, gee, our washing machine has got a 41 dB sound pressure level, and our dishwasher is measuring 41 dB, and we've got this other dishwasher that's a little bit quieter, it's at 38 dB. So what I'd like to show you is that the distortion from many power amplifiers is actually louder than these major appliances. Now, you wouldn't put a major appliance in the middle of your listening room or in the middle of your living room, but you may have something that's just as loud. So let's take a look at this. Here's a THD ratio, THD in percent versus power. These curves are published by Stereophile magazine for virtually every amplifier that they've ever reviewed. They've done a wonderful job of making measurements, and they've done this over a period of many, many years. Just a great source of information. And so we're using their numbers. I'm not using Benchmark's measurements. Even when I'm showing you our own amplifier, everything that you're going to see is Stereophile's measurements that were done in most cases by John Atkinson. So looking at this graph, the vertical axis is THD in percent. Well, what does percent mean? You know, how many percent is bad? How many percent is good? Is this amplifier going to sound good or not sound good? It's really hard to answer that question looking at this graph. The other thing that we can't answer very easily is, how loud is the noise? Everything's expressed in percent. And then along the horizontal axis, everything's expressed in terms of watts. Well, how loud is a watt? How loud is 10 watts? How loud is 100 watts? We can see that this particular amplifier goes up to 300 or 400 watts. But how loud is that? Well, let's take that same data and let's replot it. So this is the exact same information that we saw in the previous graph, but it looks entirely different. Why does it look different? So the vertical axis now is plotted in terms of sound pressure level at my listening position. And so the assumption is, we're making an assumption that I have speakers that have an efficiency of 90 dB at 1 watt, 1 meter, or more specifically, 90 dB at 2.83 volts. Okay, 2.83 volts is the voltage that would give you 1 watt into an 8 ohm load. So it's much better to look at speakers rated in terms of voltage sensitivity, their sensitivity at 2.83 volts, than their sensitivity at 1 watt, because the 1 watt is going to be dependent on what the load impedance is at that particular frequency. I always prefer to specify speakers in terms of sensitivity at 2.83 volts. So let's look at that on the horizontal axis. Now, instead of plotting power, we've got amplifier output level in terms of voltage. So In the middle of this graph, we can see 2.83 volts. That's the 1 watt level. And then you can see 28.3 volts. And that's the 100 watt level. But what's really cool is we can look at this graph and we can see the noise floor of the amplifier. And we can see that this amplifier has a noise level of about 7 dB SPL. So 7 decibels above my threshold of hearing at my listening position. So we can expect that this amplifier will make a little bit of audible noise. The audibility of that noise will depend partially on what type of noise is coming from the amplifier. Is it hum or is it hiss? So it can be either a combination of both, but whatever the case, this amplifier is making a little bit of audible noise. But look at what's happening when we get above that 1 watt level. In fact, I'll go to the next slide because this shows the 1 watt level, the 2.83 volt level, and the 100 watt level, the 28.3 volt level. But along the horizontal axis now, I've replotted it in terms of sound pressure level. So that's my listening level. That's the level of the music. At the 1 watt level, you can see that it says 90 decibels. That's because we selected a speaker that was 90 dB at 2.83 volts. At that 1 watt level, at that 2.83 volt level, our playback level is 90 decibels at my listening position. And I'll add here that the speaker sensitivity at 1 meter from a single speaker in an anechoic chamber is very close to the same sound pressure level that you're going to have with 2 speakers at a distance of 6 to 9 feet in a typical listening room. So it makes it easy to take those efficiency specifications for your speakers and relate those back to the sound pressure level that you're going to experience in your listening room. So moving across the graph to the 100 watt level, we can see that there's a substantial increase in the level of the distortion of this amplifier. And in fact, you can see that starting at about 1 watt, the distortion starts to appear out of the noise floor. It starts to ramp up. And by the time we get to 100 watts, the distortion is 35 decibels above our threshold of hearing. So if you remember back to the first slide, the 2 dishwashers, one of them was 28 dB SPL and one was 31. So we've got louder distortion than those 2 appliances, but at least it's not as loud as the washing machine. So let's take a look at what happens when we load this very same amplifier with 4 ohms instead of 8 ohms. Now what you can see with the orange curve there is that with a 4 ohm loading, there's no change in the noise floor. We wouldn't expect to see one. But as that amplifier starts working to deliver current into the speakers, the 4 ohm load is putting a heavier load on the amplifier, and as a result, the distortion is higher on this particular amplifier when it's driving a 4 ohm load. The other thing you'll notice is that the amplifier runs out of steam at a little bit lower output voltage when it's driving 4 ohm speakers. So you can see that it clips sooner with the 4 ohm load than it does with the 8 ohm load. Now here's another amplifier. Again, this one is making noise that's above the threshold of hearing. In this case, it's about 9 or 10 decibels above the threshold of hearing. But you can see a much larger difference between the 8 ohm loading in the blue curve and the 4 ohm loading in the orange curve. This amplifier is clearly struggling when it has to drive lower impedances. You can also see that distortion starts ramping up well before we even get to the 1 watt level. So even at very low listening levels, we're creating a substantial amount of distortion at our listening position in the room. We can also see that the loudest sound pressure level that we can expect to make out of this amplifier is somewhere between 105 and 110 decibels, which is respectable. You know, the target is to try to put together a system that will give you at least 105 dB peak SPL at your listening position. Now, here's another amplifier, and there's a couple of things that are good about this amplifier, and there's a couple of things that well, are not so good. First thing is that for the first time, we're seeing an amplifier where the noise is below the threshold of hearing. So we're not going to hear this amplifier when it's idle. We'll have a nice, quiet listening experience, or you know, we won't have hiss or noise coming out of our speakers. However, as we get closer to the 1 watt level, the 90 dB SPL level coming out of our speakers, at that point, the distortion is just starting to exceed the threshold of hearing. It ramps up very quickly, and by the time we get to 110 dB SPL, which is the 100 watt level, you can see that the distortion is well over 50 dB SPL. So in other words, the distortion from this amplifier is going to be louder than the washing machine, and I assume that's the washing machine on spin cycle. So you know, it's not insignificant. And what's that going to do to your music? What it's going to do is you've got harmonic distortion, which may, in many cases, sound musical, but it's going to have a tendency to change the way individual instruments sound. Every instrument is a rich composite of musical overtones, and the exact balance between those overtones and the fundamental is what makes each instrument have its unique character. That's what makes a clarinet sound like a clarinet, and a trumpet sound like a trumpet, and a flute sound like a flute. They've all got very different harmonic content. And when you start artificially adding additional harmonic content that's generated by the electronics, you may still be able to enjoy the musical performance, but that instrument is no longer going to sound exactly like it did when it was recorded. So if you're a musician and you know exactly what your instrument sounds like, and you selected an instrument because of its sound, that's lost when we're adding all of this electronic distortion. And we're also asking the music to hide this distortion that's well above the threshold of hearing. We're only getting away with this because the music has a tendency to hide it, but in the process of hiding it, it does make musical instruments sound different than they would otherwise. Now, the one good thing about this amplifier is that it has the ability to drive low impedances without changing its performance. So if you look at, there's 3 curves there. There's a curve for 8 ohms, there's a curve for 4 ohms, and there's a curve for 2 ohms. And all 3 of those curves are right on top of each other. Now, what you can see is the amplifier does clip sooner when it's driving 2 ohm load, and then with a 4 ohm load in the orange curve, you can see that it clips a little sooner than it does when it's driving an 8 ohm load. But that's to be expected. This has the ability to drive low impedances, but the distortion ramps up quickly with level. And this is typical of a lot of Class D amplifiers. This happens to be a Class D amplifier. And that rise in distortion with level, and also there's a rise of distortion with frequency that comes from a lot of Class D amplifiers. Now, Here's an amplifier that looks very good in a lot of respects, except for one thing. The noise from this amplifier is a little bit above the threshold of hearing, but has very respectable distortion performance. When we get to the 90 dB level, the 1 watt level, the 2.83 volt level, there's no rise in distortion. In fact, we don't see any rise in distortion until we get pretty close to the 100 watt level, to the, in this case, 110 dB SPL playback level. And then we see just a moderate increase in THD. Now, it does reach a level of 14 dB SPL at the 110 dB listening level. So it's 14 dB above threshold, but it's certainly not at the level of a major appliance. So I get rid of the washing machine, I got rid of the dishwasher, and now I've got maybe the equivalent of you know, a small fan or something in my listening room. So this is more respectable performance. It's too bad that this amplifier isn't a little bit quieter than it is, but it does some things quite well. So here's another amplifier. This one, unfortunately, has a very high noise floor. The noise coming out of this, this amplifier is 16 dB above our threshold of hearing. Now, and again, we're showing 3 different curves here. One is for 8 ohms, one is for 4 ohms, and one is for 2 ohms. And you can see that this amplifier really struggles with 2 ohm loading, but does quite well with the 4 ohm and 8 ohm loading. Although I will say that having such a high noise floor tends to hide some of the distortion. We have to get to a fairly high amount of distortion before it starts to appear above the noise floor. So if you extrapolate that orange and blue curve down, you can see how there is a, and you can also see it in the green curve, there is a ramping up of the distortion with level. It's just largely hidden by that very high noise floor. So here's kind of an amplifier with a twist. I call this a Class D with a twist because it kind of looks like, I don't know, a DNA molecule or something, just twisting around. But what it is it's actually a Class D amplifier with a tube front end. So yeah, you've got some things going on from the distortion caused by the tubes, and you've got some interaction, I guess, with the Class D. But what we see is that for the most part, the 8 ohm and 4 ohm loading track each other pretty well. This amplifier is quite quiet. It's only making noise at about 3 dB SPL, so this is essentially almost perfectly quiet. You're going to hear a little something if you get your ear up next to the speaker, but it's got, for the most part, very respectable noise performance. The issue is that the THD is 30 to 33 dB SPL at the 110 dB listening level. So this is reaching that level of the dishwasher, but at least when the music's not playing, the noise is at or just slightly above the threshold of hearing. Now, this is the Benchmark AHB2, which is also on Stereophile's list of recommended amplifiers. In fact, it's been on that list year after year, and John Atkinson actually described it as the lowest noise, lowest distortion amplifier that he'd ever measured. And you can see that clearly on this graph. And again, this is Stereophile's measurement data. The orange and blue curves there, which are right on top of each other, are the 8 ohm and 4 ohm measurements. And what we can see is the noise floor is 17 decibels below the threshold of hearing. So there's absolutely no possibility that this noise will be audible. And You'll also see that there's no rise in distortion all the way up to the 100 dB sound pressure level, and then we see a little step there. And what that step is actually the relays switching in the audio precision test station. This is where the audio precision test station is going into the next measurement range. And so we're actually seeing the distortion of the measurement system. And so you see that step and you see another step. Those stair steps that you see in there are actually an artifact from the measurement system, not from the amplifier itself. And so what we see is all the way up to the 110 dB sound pressure level, where the amplifier reaches the 100 watt output in the case of 8 ohm loading, or 190 watt output in the case of 4 ohm loading. Those are the blue and the orange curves respectively. There's very little difference in the clip point between 4 ohm loading and 8 ohm loading, and there's absolutely no difference in the THD plus noise when you compare the 4 ohm performance to the 8 ohm performance. And likewise, there's no change in the noise floor, but we wouldn't expect a change in the noise floor with a change in loading. Now, what's the green curve? The green curve is the bridge mono mode of operation that the AHB2 has. So you flip a switch on the back of the AHB2, and you can see that here. There's a mode switch right there. And you flip that switch and you move your cable over to this bridge mono output, or if you're using binding posts, you wire between these two center binding posts. And what that gives you is almost 4 times the power. You get 380 watts into 8 ohms. And what does that do in terms of playback level? We can look on our sound pressure level versus sound pressure level graph here, and we can see that the green curve clips at about 116 dB sound pressure level. So we've gained 6 dB higher output level by going to bridge mono. We have suffered a 3 dB increase in noise performance. You can see that the green curve is ever so slightly higher than the orange curve, but I'll remind you that it's now 15 dB below the threshold of hearing instead of 17 dB below the threshold of hearing. So the reason for that is we've taken the 2 amplifier stages and they're running in series. So we have a 3 dB increase in noise because it's random noise here and random noise here. When you add 2 purely random noise sources, the noise does not go up by a factor of 2, which would be 6 dB, but it goes up 3 dB. So we have a 3 dB increase in noise performance, but a 6 dB increase in output level, maximum output level. So what that gives us is, instead of having a 132 dB signal to noise ratio that we have in stereo mode, we have 135 dB signal to noise ratio. So we don't quite gain the full 3 dB, but we gain 2 dB in signal to noise ratio when we're running bridge mono. All of the benefit of that is the increased output level that we get in bridge mono. We have the ability to play and play cleanly 6 dB louder than we have in stereo mode. And 116 dB is 10 dB above the THX recommendation for professional post-production facilities and for large home theater systems. The recommendation is that you should be able to create a 105 dB peak sound pressure level, and here we're able to go 10 dB above that. So in bridge mono, you have a very powerful amplifier, 380 watts into 8 ohms, there aren't a lot of speakers that can handle that much power, but if you happen to have speakers that do, like we do here in this listening room, then yeah, you very much appreciate the ability to occasionally turn it up loud and without distortion. And what you can see is all the way up to the 110 dB limits of stereo mode. The bridge mono mode is right on top of those same two curves. So there's no penalty in terms of distortion. There's no penalty in terms of noise. And I'll also point out that the distortion plus noise never exceeds the threshold of hearing. So we're not asking the music to hide the defects in the electronics. The defects in the electronics are so low that there's no distortion or noise exceeding the threshold of hearing over the entire playback range of the amplifier. And so that's the difference that you get with the AHB2. We get a 30 to 40 decibel reduction in distortion and noise compared with traditional amplifiers. And you can see that clearly on this next slide. If we compare the AHB2 to these other 6 amplifiers that were all on Stereophile's top-rated list, you can see that 30 to 40, in some cases 50 dB advantage that the AHB2 has over these traditional designs. What I want to show you here is the same graph plotted in a traditional format. So the vertical axis is now THD in percent, and the horizontal axis is power. And if I go back to the previous slide, you can see, you know, it's the same data, but it's plotted differently. And there's a dotted orange line there, and that dotted orange line that's the 0 dB SPL threshold of hearing. And on this traditional graph, you can see that that's a slanted line. Because it's a slanted line, it makes it very hard to determine how loud the distortion is, how loud is the playback level, especially since the horizontal axis is power and not sound pressure level. So here we have easy to read information, which is just completely extracted from those traditional graphs. I hope that this replotting of traditional THD graphs is helpful, and I'd like you to think in terms of decibels instead of thinking in terms of percent, because percent is not a very useful unit to be expressing these parameters. And think about what it means to get the electronic noise and distortion out of the picture, so that the only thing you're left with is the distortion produced by your speakers or what's actually recorded in the music itself. So no longer have to contend with distortion and noise generated by electronics. We have the technology to reduce those defects to the point that they're always below the threshold of hearing. And that's what the Benchmark signal chain is all about. From end to end, from the DAC3 converter to the LA4 preamplifier to the AHB2, you get a signal chain that's completely transparent. And by completely transparent, I mean that the sum total of the distortion and noise is always below 0 dB SPL at your listening position. And that's what we work hard to achieve.